All right. Hey everyone, welcome to Thought Cafe's first ever live stream, Reddit AMA, also on YouTube at the same time. We are here with some experts from around Toronto that we've had the pleasure of working with on our last video and spending some time with recently. We have Matt Russo right here. He'll introduce himself after I'm done. Andrew Santaguida.
Nailed it.
And Dan Tamayo also here as well. So they'll be talking about the stuff that they're answering on Reddit. You can go find the link in the description below. Get onto Reddit right away and start checking out the questions they're asking. Ask a question there or ask a question in the comments below. And they'll be answering them for you. We'll be on here for about 30 minutes or so, and it should be a lot of fun. So why don't you guys start off? Matt, with you, you can just introduce yourself and what it is you do.
Sure. So I'm an astrophysicist at the Canadian Institute for Theoretical Astrophysics, and I study how planetary systems form, how planets form out of disks of dust and gas. And when I'm not doing physics, I'm a guitarist. I did a degree in jazz guitar before I got into this whole physics thing, and I play in a band called Runners with Andrew.
I'm Andrew Santaguida. I'm a piano player. I did classical performers from the conservatory. And I play with Matt, and I don't know anything about astrophysics, but here I am.
I'm Dan. I work next door to Matt at CEDA, and I'm also at the Center for Planetary Sciences here at the University of Toronto. And I get excited every day about these residencies. So it's been a really fun project to put this together and put everything to music and look at this problem in a completely different way.
Awesome. So I'm just gonna throw some questions out there. Let's just start with, for all of you, including you, Andrew, because you're friends with these guys, but also it's a good example of sort of the general public. When the information about TRAPPIST came out, how did you all feel?
Well, I'm kind of a little cynical, I guess. So or jaded, I guess is a better word. So when I first heard it, it didn't seem like that big news to me, because I know we found 4,000 other planets. Some of them are Earth-sized. But I started hearing about it from my family, which is weird because I don't know anything about science and space, and they were excited. So I looked a little deeper, and that's when I saw the most. Now I know about an endless number of remarkable things about the TRAPPIST system. I was so foolish.
Yeah, I first heard about it just through social media and everyone just being really excited about it. So I naturally asked Matt, and he's like, "Oh, there's 4,000 of those." So I was a bit tampered after that, but I don't know, it kind of really got really exciting. And Matt came around and he started looking into it more, and it seemed really cool. And NASA really got on board with it. They released a lot of cool artwork with it, which doesn't really happen. So you kind of knew that it was different.
So I think that the coolest thing about the TRAPPIST system is, we found lots of big multi-planet systems like this with previous missions, but those tend to be really far away from us. They're hard to study. So this one is about 40 light years away. It's one of the 300 closest stars. So that means we can really go with the next generation telescopes and study their atmospheres. So they're ideal targets in looking for signatures of life on other planets. I think that's driving a lot of the excitement. It's just an unbelievably lucky system to discover. So really exciting.
I think you also hear about once in a while they'll find a planet that's habitable however many light years away, but never a system with that many planets around it, which seems to help it a lot.
That's cool. Dan, what's the best question you've gotten so far on Reddit?
Yeah, so maybe we could talk. I think the highest rated question is a really good one, and maybe that's a good one for discussion. And it's this. They bring up that there's been an article that says, well, we shouldn't be so excited about the system because these low mass stars, they're going to have lots of X-rays, they're going to have lots of flares, this is going to be terrible for life. So so maybe this isn't as exciting as everybody else thinks. So that's obviously something that really interests lots of people in the scientific community. A lot of people are working on it, but maybe it's just sort of like bigger picture is something that we could talk about is that, this search for life outside the solar system is something that's, driving a lot of the field. NASA's really interested in astrobiology. And the goal, the strategy has always been to look for life that's similar to life on Earth, right? So we look for planets that have the right temperatures, that have water. We look, for low X-rays. You want it to have an atmosphere. And that makes a lot of sense because we know how to look for life that looks like our own, and we don't know how to look for life that we've never seen before. But I think one really exciting thing about TRAPPIST is that, this is a system that we can really study with our telescopes, and we have 7 planets that have a range of conditions on them. If maybe on the innermost ones, maybe they get bombarded by X-rays and you're not going to find Earth-like life on it, but maybe you do find life below the surface. It's just an opportunity to learn so much about new planets and learn new things that we wouldn't have been creative enough to think up ourselves in the first place. So I guess my response is more like, maybe we're not going to find humans on TRAPPIST, but we're just going to find there's just the potential to find so much more.
Yeah, especially because most stars are more similar to TRAPPIST-1's weird system than ours. About 75% of stars are called M dwarfs, so they're cool and red. And until now, we've kind of been neglecting them for good reasons. They're hard to study. They're hard to find planets around in some ways, but they're also make it easier to find smaller planets because the actual size of the star is kind of small. Makes the planets in front of them look a lot bigger. So a lot of people are turning their attention to that in the next few years. There's several missions planned just to look at planets, to find planets around cool red dwarf stars. Because now that we know that planets can easily form around them, it strongly implies that most planets are around cool red dwarf stars.
Nice. And Matt, I'm going to ask you a question, then I have a question for Andrew that's coming from YouTube. So why did you decide to study space or astronomy or get into astrophysics?
I kind of discovered, I was always really interested in math just for its own sake, and then I got to a grade 11 physics class and just felt like I understood the universe for once. And it just really, really captured me. I've always been interested in space and science. My dad had a big part in that. He always shared science books and science documentaries with me as a kid, and it was just fascinating, and I never lost that.
Nice. Some people are commenting that you kind of look like astrophysicist Tony Stark.
Tony Stark.
That could be
Iron Man.
some Iron Man. Yeah.
Oh, Robert Downey Jr.?
Yeah.
Okay, I'll take that one.
So Andrew, I have a question for you that's interesting, and I know it's discussed a lot in sort of your discipline, but this sort of relationship between music, musical notation, musical structure, and the sciences. Can you talk maybe a bit about your thoughts on that, and specifically sort of like how these types of relationships can come about?
You mean like?
Just how a lot of people talk about youth, going into music programs will also help you in mathematics, will also help you in sciences. There's a lot of correlation between the structure, and clearly there's a lot of correlation to what you're working on and how this project came about.
I think they kind of grow in the same way. Like when you first start learning an instrument or learning how to read music, you just you learn the basics. You learn what the notes are, every good boy deserves fudge and all the little things. So it's kind of the beginnings of math, and then as you get more advanced and learn about the different chord structures, it kind of just I find it grows in the same way that you would learn the basics of math, and then that kind of grows to build more and more. And I think they kind of use the same part of the brain in a way too.
Nice, that's great. How about let's talk about the distance. I know, Dan, we had talked about this before. People are asking fairly generic, how long would it take to travel to TRAPPIST, but using the fastest method of transportation we currently have.
Let's calculate this. I get 120,000 years.
Wow.
Yeah, it's the problem, right? Stars are really, really far away. Well, so maybe I'm not totally up to date. So that's assuming that you go to Jupiter and get a gravity assist from Jupiter, and then you leave the solar system. That would take sort of 100,000 years. But there's a lot of work at NASA. The nice thing in space is once you get going, you don't slow down, right? So they're working on like these ion engines that just slowly speed you up. But then you only get to accelerate half the way, because then you need to make sure that you stop before you arrive. So it's not in the near future to go to these systems. But one cool thing with Proxima B is there's like a big initiative to actually try to send really small spacecraft there. They like make these sails on these tiny spacecraft, and then they like focus, I don't know, like 100 enormous lasers on that sail to speed it up. Yeah,
That's called Starshot.
yeah. To like a fraction of the speed of light. So that would be amazing, right?
Aren't those things just like nuclear bombs?
Yes,
though?
that's the problem. You'd have to send like a swarm of like 1,000, because a lot of them are going to get destroyed on the way when they run into particles, like random dust particles in the interstellar medium. But then if one of those, like even if it's like 10 grams, if it's traveling at almost the speed of light and hits a planet, it's, I forget the number, but you can probably calculate it in 3 seconds. The equivalent of several nuclear bombs.
Yeah.
So we got to be a little careful where we send them.
Right. So like if there's aliens on Proxima B, start seeing all these things coming, you could imagine that they won't interpret it as friendly scientific exploration, but like projectiles coming at you that could wipe you out completely. So Thought Cafe actually has a really cool YouTube video on Proxima B. So I'll just link that in the comments on YouTube. Let me do that really quick.
I think it's interesting, actually, that whole sort of speed situation, and not wanting to maybe pollute another planet or moon with a satellite or something that we've created. I know this has become more of a relevant issue recently.
Oh yeah.
With
The moon, like Enceladus.
yeah,
and
exactly.
Saturn.
Do you want to talk about that maybe just briefly?
Sure. In case anyone doesn't know, there's 2 moons in the solar system that I think would be our best chances for life outside of Earth in our solar system. So Europa is around Jupiter, and Enceladus is around Saturn. They turn out to be very similar to what we think TRAPPIST-H looks like. That's the furthest one out, and we know it has a lot of water, but it's too far from its star, from TRAPPIST-1A, to be liquid, so it's probably got the surface entirely covered in ice. So that's the way Europa and Enceladus are. And so there could be life, in the oceans. There's hundreds of kilometers of oceans on these moons. There's more water on Europa than there is on Earth, for instance. And luckily, some of it is getting sprayed out of the planet in geysers. There's kind of cracks, and pressure builds up, and it sprays these geysers into space. And so we've been flying probes through those geysers to collect it. And there was a discovery a few weeks ago. I forget the details, but they found some elements that seem to be consistent with some kind of lifelike processing. Maybe I'm going too far. Do you remember?
No.
Okay, so we can find
I
a
had a
link to
child a
that.
couple weeks ago.
How about with regards to this video and the musical process? Someone's asking about how the music respects rhythm, but not necessarily musical ratios. Would you say that's correct or incorrect?
By respecting musical ratios, are they addressing the tuning issues?
Maybe, yeah, that seems to come up quite a lot.
Yeah, I'm actually just about to answer that question.
Nice.
So I can't put web links, web URLs in the live chat, but
Okay,
if you just look at it.
I think I can do it.
Oh, okay.
Yeah.
Okay.
It kind of respects the tuning of TRAPPIST. Like, it's not Western tuning. Like, Western tuning would be like, you keep like A440 and you just go up and down from there. And this one takes like the resonance, like when you set it at C, planet H, and then just extrapolate. It kind of keeps how out of tune they are from each other.
Yeah. It's really remarkable to us how close to being in tune they are.
Yeah.
So these are 7 planets, 39 light years away. And most systems aren't anywhere near as harmonious as this. Right? You might know we we tried Kepler 90 as a kind of an example, like an anti-TRAPPIST, because it has 7 planets, but none of them are in resonance. Maybe one, but that wasn't enough to save it. It just, I'm still like recoiling from how bad Kepler 90 sounds.
Yeah, so that's like feedback that I feel like we've gotten a lot. And, you know, people have done that before. You know, like there are lots of clever ways that you could sort of translate the motions of planets and make really awesome sounding music. But I feel like the cool thing about this is that we did very minimally, you know, we did very, very little of that. You know, so if you take any of these other systems that people have looked at before and you just ran it in the same way as us, then it would just sound terrible. But it's the very special configuration of TRAPPIST that it's just amazing that it sounds even remotely pleasing to the ear.
Yeah, that doesn't stop people from complaining on YouTube though. But yeah, you got to keep in mind that your ears can be trained, right? There's other musical cultures where they're completely used to things, to quarter tones and things being slightly out of tune, and your ear just develops. So, you know, listen to some more music if that bothers you.
More planets.
Cool. So what about on Reddit right now? So the subreddit you guys are currently answering questions on is Ask Science. Do either of you have any experience with that before, or what the process has been like so far?
I have never done.
Okay, that's fine. Yeah, so let's talk a bit about, Dan, maybe about the crazy amount of simulations you were doing and what exactly you were doing in as much of a general way as possible, and then how, you know, Matt came by and that sort of happened. You guys realized, oh, this could really work in music.
Sure. Yeah, so like in the sorts of things that we do, we're always completely limited in how many computers we have available and how long we can run them for. So we're really lucky at CETA, this Canadian Institute for Theoretic Astrophysics, that we have this supercomputing cluster, which lets us run, you know, hundreds of simulations at the same time. We have to share it with everybody else at CETA, so I think everybody at CETA now hates me because, like, in the queue of all the simulations, it was just D tomato. But yeah, that allowed us to try a whole diversity of TRAPPIST-1 type systems that simulate a range of formation conditions, you know, and learn something a bit more general than if we could just do one. But, you know, we basically integrated for each of them took about a week to run. The ones that we took that we ran for the longest times. So yeah, it's a big computational crunch.
Sweet. Talk a bit about, like, I know we've talked about it before, Dan, but sort of like, obviously in your paper and a bit in the video we made, you talk about how the orbital resonances help stabilize the planets. Maybe talk a bit about why that's important as far as them being potential candidates for life.
Sure. Yeah. What I find fascinating about these resonances is that they can be great for keeping things stable, and then they can also be atrocious. You know, resonances are also responsible for why the dinosaurs went extinct. If you look at like the asteroid belt, then at locations, you know, as you move away from the sun, then things orbit slower and slower. So there's locations at which asteroids have resonant period ratios with Jupiter, right? That it might go around 3 times for every 1 orbit of Jupiter. And a lot of those locations in the asteroid belt are empty, right? So those are actually like escape hatches from the asteroid belt that bring asteroids onto Earth crossing orbits that hit us and do bad things. And then on the other extreme of that, in terms of the opposite behavior, if you look at Neptune does 3 orbits for every 2 orbits of Pluto. And that's the only reason that Pluto's alive today, because their 2 orbits cross one another. So if things were just random, eventually they would come at the same place at the same time, you know, and Pluto would have been demoted to interplanetary dust, and it wouldn't exist today. So in that case, it really is this very precise 3:2 period ratio that keeps that orbital configuration repeating like clockwork, like music, that keeps things completely stable. So for the paper, you know, what determines which of those 2 cases you're in is actually not just the period ratios, but how well you tune all the additional orbital parameters, like how elliptical the orbit is. So that's the difference. In the original paper, we don't know a lot of those parameters very well, so when those things aren't tuned, you don't get a very harmonious system. Things blow up very, very quickly. It's like why the dinosaurs went extinct. But in our case, by simulating the formation, we could actually naturally tune the systems into these stable Neptune-Pluto-like configurations, and then that we found really, really helps stabilize the system and makes it possible for it to survive to the present day for us to find it. So.
That's great. Matt, what kind of question are you working on at the moment?
I'm working on a related question. Someone's asking, is it just a lucky coincidence that these are all in resonance? And so, or is it just a happy celestial accident, as they phrased it?
Nice.
And so, obviously, this is Dan's area of expertise, but the basic idea is that planets can migrate when they're first forming. The planets are still inside a disk of gas. They can interact with the gas, and the gas can interact with the planets, and can kind of make them either spiral in a little or spiral out a little, depending on many very complicated factors, like the temperatures and the masses of the planets. So that just lets planets move, and if they're moving slow enough, they can get kind of locked into this stable pattern, and then the gas disappears, and the planet system is exactly how it was locked. So we knew about planet migration, I think, since the 70s. Goldreich was the first to point it out, studying Saturn's rings, actually. But we expected when we found planets that a lot of them would be in these resonances for that reason, because we expected them to be moving into them and get stuck. But out of the planets we found now, the vast majority are not in resonance. There's a slight excess in some of the resonances, or just outside of them, actually. But it's kind of a mystery. And so it could just be that the disks they form out of are too turbulent, so the planets are kind of getting jostled out of these resonances, or they're moving too fast and they kind of like skim over them, kind of like a car going over a pothole really fast. You just kind of go right over. But now that we found TRAPPIST, it kind of changes things, because we haven't studied these cool red dwarfs that much yet. And so if we found this one, you know, I liken it to picking up a few dozen rocks and finding one solid diamond. The other rocks are still pretty cool, but we don't know how common this is. So in the next few years, we'll find many more systems around red dwarf stars, and maybe this is more common around red dwarf stars, because maybe their disks are a little calmer than brighter stars.
I'm going to ask a question about music to you, Andrew, and then we're going to come back to something about red dwarf versus white dwarf kind of stuff.
Yeah, we should answer the solar system question.
Yes,
A lot of
that's a
people-
big
Yeah.
We get
We'll
that
jump there.
all the time.
Andrew, talk a bit about the type of sort of remix ideas and stuff that's been coming out through the community through sharing the music that you guys did around.
So So we have like the MIDI data from what we did. So like the note that it's on, not like the tuning, but like the note it's on, and the rhythmic patterns. And we've made that available, so anyone can kind of get that from our website. And you can kind of just like, we just chose to put it on a piano and like the conjunctions on a drum. And you can kind of just take it and put it wherever you want. So everyone can just kind of like take the rhythms and put them on like a different instrument even. Or like, don't use a piano and use like a sitar, so it should sound out of tune. And just like, you can just turn it into like something completely different. You don't have to use like the arrangement we did. We just like arranged it to like stagger in, but really it just started out as just like a smattering, like everything just all at once.
Yeah, a lot of people have noticed that I've spoke to that, as it begins and you're hearing each planet come in and then it slowly builds up, at first you're kind of like, oh, like, this is kind of whatever, but then very quickly it actually starts to become music, and at the end it's almost this beautiful chaos.
Yeah.
Mm-hmm. Yeah, like when Matt first showed it to me, he just had it just on a piano, and it was just everything at once happening, and it sounded really like a Steve Reich kind of thing. Like he's a composer that does this kind of thing, and like it already sounded pretty cool.
Sweet.
So it just took like a bit of arrangement on our part.
Yeah, I also find like you really notice the tuning early on, and it's very unsteady. But then once everything's in, I don't know, all the different tunings kind of cancel out and it becomes more stable somehow.
Yeah.
I don't know what's going on there.
No.
Sweet. There was one question about white dwarfs and whether or not there's any new theories or studies with regards to potential planets around those versus red dwarfs, which is what we were talking about earlier.
Sorry, you're asking
Do you
about
wanna
white
take
dwarf?
Yeah, just
Uh-huh.
versus like, the smaller red
Yeah.
dwarfs that you guys have been talking about. Do you anticipate similar formed systems, or is it going to be much different?
So astronomical nomenclature makes no sense, right? So red dwarfs are like this low mass end of stars. White dwarfs are actually what you get after a star dies. So it's like, if you take our sun, once it runs out of hydrogen to fuse in its core, then it'll blow up, blow up's the wrong word. It'll expand into a red giant, and then once that phase runs out, it'll lose its outer layers, and you'll just be left with a really hot core, and that's a white dwarf. So they form in really, they're sort of really different, right? So like in TRAPPIST-1, here you have lots and lots of planets super, super close to the star. You're never going to find that in a white dwarf because if that's where the planets are, they would have been completely engulfed in the earlier red giant phase. But I guess one really interesting thing that people have been finding recently, and there's a lot of excitement with around white dwarfs, is that if you look at the atmospheres of white dwarfs, so stars have atmospheres, you find lots and lots of heavy elements, things like carbon and nitrogen. And that's a really big puzzle because those are heavier than hydrogen and helium. They should sink to the center. So the fact that you see these in the outer layers of these white dwarfs means that stuff is continually raining down on them. So obviously they're really active systems, and there's a lot to learn from them. I think that's sort of what attracts me to astronomy. That it's just things that we'd never be creative enough to think up ahead of time ourselves. The universe is just full of surprises, and then it's a matter of trying to put the pieces of the puzzle together and figure these things out.
Cool. I know you guys have brought up a question from Reddit right now about the solar system.
Mm-hmm.
Do you want to answer that possibly?
Sure. So yeah, TRAPPIST-1 was kind of low-hanging fruit, like because of these resonances, like it sounds as good as any system could sound, probably, with as little input as we put in. People have been, the word is sonifying or sonification. People have been doing that to the solar system for, I guess, centuries. It probably goes back to Kepler, who's the first one to try this. People have been doing it, but because the planets in the solar system are not in resonance, except for Neptune and Pluto, if you count that, they're not as close to standard Western notes, and the rhythms are not exactly repeating. So you'll get some kind of rhythmic pattern, but it'll be shifting over decades or centuries. We're trying. We're gonna do a version of it. But the cool thing is that, or the interesting complication is that there's a much bigger range in frequencies between Mercury and Neptune than there is in the TRAPPIST-1 system. So when we scaled the TRAPPIST-1 system up into the human hearing range, it was in a pretty normal, it all fit in a pretty normal range of musical notes.
It's just like 2 octaves or something.
A few octaves, yeah.
Yeah.
But the solar system, the range between Mercury and Neptune is pretty much the range of human hearing total. So like the lowest note is kind of like a thud, but you can kind of hear it, and the highest note is like this really high-pitched dog whistle, and you kind of hear it if you're below the age of 25. So we don't want to exclude older people like us. So we're going to have to find some creative solution to do the solar system. We're really excited that I think you'll love that we can't share right now. But it's coming in the next month or two.
Nice. Yeah. That's cool. I know there's often a lot of questions that we see online, just in discussion, where people sort of ask about, like, can we make assumptions that if, you know, a system has carbon content similar to our own, that life would develop? What are your guys' thoughts to that?
Well, I think, it's always dangerous to generalize from a sample size of one, right, with the planet, with the Earth. But at the same time, life could have started on Earth at any point in its history, right? But when we look back, we basically find that life got started just about as soon as the conditions on Earth were, not getting continually bombarded by planet-sized things that would melt the entire surface. So that seems to suggest that once you have reasonable conditions for life, that it's fairly easy to get it started. So I think that's like an encouraging piece of evidence in trying to think about or look for life elsewhere in our galaxy.
The other thing, like my favorite statistic about exoplanets and life right now is that, so we found about 4,000 exoplanets, and that's enough to start doing statistics and to find out how common Earth-sized planets are around sun-like stars. And so in the last few years, they've really narrowed down, or they've come up with a number for the first time, and they've calculated there's about 10 billion Earth-sized planets in the habitable zones of sun-like stars in our galaxy. Okay, so our galaxy is 200 billion stars, and they estimate that there's at least 10 billion chances for life, life as humans know it. And then there's, I think, another 6 or 8 billion more around red dwarf stars, like the TRAPPIST system. So that's even being conservative in some ways, because that's not counting things like moons of gas giants, like Europa. If life can exist on moons of gas giants, then there's probably many, many more chances for life, if you count that.
Now, I know oftentimes when people talk about like Drake's equation and things like that, they also mention that those 10 billion plus 6 to 8 or whatever billion possibilities, what are really the chances that those are happening around the same time, that those places, those forms of life might actually interact or intersect in some way or discover each other?
Yeah.
What do you guys think about that?
Yeah, I think that is like one of the most uncertain terms. Well, so Drake's equation is it's just a simple way of trying to estimate how many alien type civilizations you might have in the galaxy. So you might say, well, start with how many stars you have in the galaxy, then what fraction of those have planets, what fraction of those would develop life, and you just try to figure out each of those factors. Right, so as John was saying, one of the most uncertain and most important factors in there is once you get to human-like life, what fraction of the total time do they survive for? Or do they elect Trump and then destroy the entire planet and then they don't exist anymore? Right? Because if you think about the entire history of the Earth, humans have only been around for the last, the right comparison is, at what point were humans able to start sending signals out into space? So that's like in the last 100 years, maybe with radio, right? So that's 1/10,000,000th of the age of the planet. If we elect Trump and then we have a nuclear war and then everybody dies, then you have to get super lucky for two civilizations to be around at the same time. So yeah, I don't know the answer to that. Right? I think maybe this is where it's fun to speculate, right? Like you think what would determine a lot of this is, can civilizations get to other stars before they start blowing themselves up? Right? Because once you diversify and are in a couple different places, it's going to be much harder for you to completely destroy yourself than when you're stuck with one planet, right? Because if we let global warming go and we destroy our own planet, if we don't get off it first, then that's it for us.
That's fun.
Yeah.
Great. And maybe you guys talk a bit about sort of the moves NASA's making, but also private industries making towards Mars. This, Mars is this big, exciting thing, becoming interplanetary. What do you guys think about that?
It's exciting in some ways, right? We haven't had like a real space age like that since the 60s. There's most of you are probably aware there's some serious challenges with setting up a colony on Mars. The biggest one is probably the intense radiation, right? Mars isn't protected as much as the Earth from the solar wind and solar radiation because it doesn't have a strong magnetic field. So they'd have to find some kind of magnetic shield. Maybe they can, burrow deep underground or get some kind of electromagnet. But, just personally, I mean, it's just, aside from any kind of political issues, I'd just be so excited to see that, like anybody else. I think it also inspires the next generation, right? That's the usual justification for things like this. One of them is that it's, people are aging and we have kids that are going to fill our place in the future, and we want to inspire as many as possible. So we have the biggest pool to work with, and we can discover the most.
Yeah. So I think Thought Cafe also has a really cool video on, like, could we live on Mars? So that'd be cool.
Yeah.
I think like one really sad statistic is that like humans have been to the moon. We've done all these amazing things, but if you look at since 1972 or something, the last time that we went to the moon, no human has been, if the Earth was a basketball, no human has been more than like a fingernail width off the surface. That's super sad. And I think that like SpaceX and these private industries getting into this is absolutely crucial, right? Because you think about NASA. NASA's this like huge government organization that relies really, really strongly on public funding. So that means that they have to be extremely, extremely risk averse. Every rocket that blows up for NASA, or like if astronauts die, that's a huge crisis. And then everybody starts asking, well, maybe we shouldn't be investing all this money in a space program, right? Like, well, why are we even doing this? But once you bring industry in that can have, that has business interests in going to space, then you really start moving things forward, right? Right, because SpaceX can take bigger risks than NASA will ever take. That means that they can drive down costs for going into space by enormous amounts. It changes the game completely. So I think that we're in a really exciting phase. I always like to imagine what it must have been like growing up in the space age, going to the moon. But I think we're heading in that direction, and I can't wait to see how that goes.
I think it's something you can get like everyone on board with too. Like that really unify a lot of people. Just knowing someone going to Mars. That's like
Absolutely.
Yeah.
Cool. Well, we can wrap it up there. Do you guys have anything last you want to say before you get back to finishing up those answers to all those questions you have on Reddit?
Keep the conversation going
Yeah.
on Reddit.
Yeah, and
thanks for watching. And
yeah, thanks a lot. Really appreciate it. You can contact us in many different places. system-sounds.com or through Thought Cafe or through our Facebook pages or Twitter. We'll answer.
yeah.
Awesome. Well, thanks so much, guys. And that's it for today.
Boo.
We have
Booming's done.